Good day. Today we will tell about the elementary translations and space lattice. Also, the empirical laws of crystallography, they are very important for understanding of this topic. Here you can see the plan, basic determinations per crystal lattice, the Stennon's law and the Wolf-Braggs conditions. Here you can see the representation of the crystal lattice. We consider an ideal crystal in structure has no imperfections. All identical particles are arranged in parallel infinite series. The distance between particles in the majority of crystalline materials is 10th nanometer. In other words, about more than 1 million particles are distributed in the length of 1 millimeter in the crystal, which can be regarded as an infinite series. So the shortest possible distance between identical points in a series is called a translation unit or a period of identity. If you sheet the point of an infinite series for a period of identity, a series aligns with itself. It is a symmetrical translation by which the point is repeated in space. Here you can see it. This transformation is called translation. Repeating any point using translation, we obtain the infinite periodic series of identical points on the distance a2, a3, a, and etc. The same points interconnected with translation are called nodes of the series. A site doesn't necessarily coincide with the material point. It is important. If you repeat the same point with the help of another translation, that it is not parallel to the first one, as here, you will obtain a flat grid that is fully determined by the two translations A and B. Parallelograms with vertices at the sides are called mesh grid. We choose a unit cell in a flat grid. Repeating it with the help of translation, we obtain a flat grid filling the entire planes without gaps. A unit cell is chosen so that it meets the following condition. The first, it will reflect the symmetry of the grid best. It will have the right angles if possible. And the third, it will have the smallest. Here you can see the basic determinations. What it is the elementary translation, what it is the translation, and what it is unconplanar translation. These determinations are very important, so it is necessary to remember that. What is the elementary cell? Elementary cell is named a primitive cell if there are not any nodes inside her. Very important parameter of elementary cell is a reticular density. A reticular density is the number of nodes belonging to this elementary cell completely. Now we'll consider 3-point non-complanar translation. Here you can see A, B, C, which do not lie in one plane and repeat endlessly in space. We obtain a special lattice, three-dimensional system of sides. three translations, A, B, C. A translation group can be chosen differently, but the principles are the same as in a selected translation of a planar grid. Parallelepiped constructed on three elementary translations A, B, C is called the unit cell. As in the planar grid, the volume of the primitive unit cell does not depend on its shape and is a constant value for the lattice. It is equal to the volume per one side. It is necessary to remember that the space lattice is a speculative construction that serves to describe the crystalline structure and reflects its symmetry. And it's very important, the spatial lattice can coincide with the real structure, but may not coincide with one. Now I wanted to tell some words about the very important law of crystallography, the law of Stenen. In all crystals of that substances, the angles between the corresponding faces are constant under the same conditions. And the same conditions are the same temperature and pressure. This is a quantitative law of crystallography opened by Nicholas Stenen in 1668. It is the first and the most important law of crystallography. The another name of this law, the law of constancy of angles. The law of constancy of angles makes it possible to reduce all the variety of forms of crystals to a set of angles between faces and to represent them with the help of projections. This law has played a prominent role in the development of crystallography. And the of crystallography, the Wolff-Bragg condition. Before the discovery of X-ray diffraction, all crystals were characterized and distinguished from each other only by the angles between the faces. At that time, the main method of diagnosis was to measure the angles with a goniometer. Now these angles are measured using X-ray, and it is sufficient to have not a large crystal with a regular face and a small grain, but only small grain of the substance. As the wavelengths of X-ray are commensurate with the interatomic distances in the crystalline materials, they are the natural diffraction lattice. And now you can see the equation of Wolff-Bragg condition, where d an interplanar distance, n is an integer, lambda is a wavelength, and theta an angle of reflection. This equation expresses the Wolff condition opened independently by Wolff and Bragg in 1913. Please remember this.